About to add some nitric acid to the crushed up neodymium magnet. So this is 20% nitric acid by weight. I'm going to add a tiny little stir bar. And I will come back here in a minute when I've got this thing on a hot plate, stir plate. Hot stir plate. Here's the setup that I'm using for the dissolving the magnets in the nitric acid. Here's kind of my little bit of nitric acid that I pull from here. It's just 20% by weight, nothing too crazy. I've got a heating stir plate, and then I just use this Teflon beaker vessel. There's from the last dissolution that I tried. I've got some junk left over in there. It's kind of hard to see, but yeah, it works surprisingly well. And initially I thought that I would have to crush up the magnets sort of to get them close to a powder, so that way they would dissolve well with a lot of surface area. And I tried using this pestle and mortar, but did not go too well. And so I just tried a chunk, a small chunk, maybe a few hundred milligrams, and it dissolved really easily, which makes me think that this stuff must be quite porous, and I'm guessing it's because they probably make it in sort of a, they make these magnets in kind of like a ceramic sintering pressing type of process. I'll have to look into it, but I'm gonna throw a couple of these pieces under the microscope to see if we could see some of the sort of porosity and whatnot. But anyway, point is you don't, if you want to dissolve these, you really don't have to crush them up too much, which is nice. Well, can't really see pores too well with this setup, but you can tell that it's a pretty rough, grainy surface. So I'm guessing that's the surface area is pretty high, which is allowing for that nice easy dissolution. So I've got these things spinning down a little bit in the centrifuge. This centrifuge isn't exactly the best on safety, because you can actually open it while it's running, but it's kind of cool because you can see it working. So let me see if I can get this to decelerate. So here's kind of what it looks like. And here's the samples. You can see that nice purple color of the neodymium. This is the first dissolution that we tried with just a tiny little chunk of the magnet. And then the second dissolution, where I tried to see how much I could saturate, basically added like over a gram of magnet to about 10 grams of 20% nitric acid. So this is a lot more concentrated. So I'm just spinning these guys down. Here's what it looks like. If you turn it on and it just starts accelerating. So I'm going to leave that running for about 10 minutes. So here are the spun down samples. The one on the right, again, was the first go around, just trying to see how well the magnet piece would dissolve. And I'll do some rough yield calculations to see if we are getting kind of close to the numbers that are in literature for the neodymium kind of weight percentage composition for these magnets. And the left one that I really put a lot of material into concentration wise, I think it's so red because of all the iron in there. It should be iron 3 oxidation state, I think, if I remember correctly. And you can see the iron in the absorption spectrum. The way that I'm quantifying this, by the way, is kind of funny, I think. I have this older absorption spectrometer. Let me get this light out of the way. And it's normally used for microplate reading. For bio stuff, you have these plate cultures. I've got this one drying from before. These microplates that you can put cultures in, or maybe solutions with protein, DNA, whatever. And then you can read each well to get your absorption spectrum. And this thing goes from 200 nanometers to 1,000 nanometers. And you can do it in 1 nanometer steps. So I'm using it in probably not the standard way that it's made for. But I'm still using these plates. I just put in my solution of neodymium magnet and then read those absorptions and essentially get a graph that kind of will look something like this. This is from a literature of some Japanese scientists that did a study on neodymium specifically. And this is an absorption spectrum that they got that I just printed this out for my own reference. And anyway, the way that I'm quantifying this is I also have a neodymium standard. Essentially, that's 1 milligram per milliliter, I want to say. And so I'm using that to compare against my solutions. Yeah, it's 1,000 micrograms per milliliter is the spec, which translates to 1 milligram per milliliter. And it is in 5% nitric acid. And yeah, when I did the spectrum, it's actually pretty cool. I'll show it a little later. It totally matches the neodymium, and then I have a couple of extra peaks which at least from what I've seen in literature match up with that iron 3. The other thing I think would be boron, if I remember correctly, because these magnets are essentially they will sometimes have a little bit of extra, but generally it's boron, iron, and neodymium is what makes up the magnets. Yeah, neodymium, iron, and boron. And I don't know if I'm going to see any peaks from the boron in this range. I still need to look into that. I was mainly just looking at the iron and neodymium, which definitely showed up. And so using the standard absorption, the standard absorption as well as the sample absorption, I should be able to create sort of a calibration curve of concentration of neodymium in the solution and then back out how much I was able to dissolve into the nitric acid, and then back calculate essentially based on my sample weight the composition of neodymium in the magnet and compare that to literature, see if I'm getting close or if I'm way off. So here's kind of what the what it looks like when I'm getting the data. So here's the best one that I've done so far. So this is the control software basically for the spectrophotometer, the microplate spectrophotometer. And you can see the 96 wells that it scans. Each one gets its own graph. It's kind of hard to see the peaks. Some of these are blank. They have nothing in them. Basically, this is the absorption spectrum of the polystyrene material itself. And you can see that it does pretty badly in the ultraviolet range here. But anyway, if we put these on a log scale, you can see the peaks of actual samples and stuff that I put. So mainly with the water, the blank water just has this kind of infrared tail absorption here versus just the polystyrene of the plate itself has this peak here and all this stuff into the UV. And then my actual samples, I've got some with just nitric acid. And then I've got the sample itself, which we can see neodymium peaks here. Actually, it's these main ones that are the neodymium peaks, these four. And then this is iron, and it's there's also some stuff from iron going on over here that's not so obvious because right now it's mixed with the polystyrene peak along with the nitric acid. But if you do peak subtraction, then you can really see that pop out. And here's the neodymium standard. Here's those four major peaks again that we're interested in. This stuff too, but this kind of overlays with the polystyrene peak, so it's not as good to use. Okay, so now if we graph the actual data, start looking at some plots, we've got, this is the neodymium standard, is kind of what it looks like. So, but this includes the 5% nitric acid along with the, the well plate bottom itself, which then gives you the stuff in the UV. So here's what some of the graphs of interest look like. I've got the neodymium standard solution average. This stuff to the left, not super interested in. It's polystyrene and nitric acid peaks. Basically the 200 to 400 nanometer region. And this I did 3 wells with the 100 microliters of the neodymium standard. So this is the average of those 3. But what we're interested in is this area right here, basically. So these are the neodymium peaks. We've got one at around 575 nanometers, then a double peak 523, 512, then 740, another, it's like 790, 780 usually, so around 800, and then this double peak as well, but part of this is from the polystyrene. But neodymium does have a peak around 860-ish. It's just it's overlapping with the polystyrene peak. That's why we're getting this little double guy here. So that's the standard, and here are the samples. So I overlaid the standard as well on this graph, just so you could see the different peaks. And maybe it would be better actually if I just did this. So sample 1/2 refers to the sample is diluted by 2. So taking it from 20% nitric to 10%, and then 1/4 is diluted by 4. So from 20% to 5%. And the reason I was doing that is to get close to kind of matrix matching, meaning, my standard solution is in 5% nitric acid. So if I want to use the absorption to be able, the peak values to be able to quantify the concentration of neodymium in an unknown sample, then I need to match the overall solution. So my sample needs to also be in 5% nitric acid. So that's why I'm messing with these dilutions. But for now, we are just qualitatively looking at the peaks to make sure we kind of have similar peaks in similar areas. So I'm going to get rid of this graph. We'll just do those two. So here is what it looks like. So again, this stuff to the left is polystyrene and nitric acid. Now, I couldn't subtract the background from the neodymium standard because I don't have a good enough 5% nitric acid solution yet to be able to do that with. But I was able to subtract backgrounds for my actual sample, and that's how I got this. And so you can see that over here we've got stuff going on with the nitric acid and iron, especially this peak here. What is this, around 440 nanometer? This is very much to do with iron 3, at least from what I see in literature. Now, the cool thing is if we look in this region, basically all of our peaks line up. So we definitely can confidently say that there is neodymium in this solution for sure. Here's this double peak, this peak, this one, and then even this one over here, which in the standard solution, it's got the overlap with the styrene. But here, because the background is subtracted, we've only got the neodymium peak that's right around 860, which is exactly what we expect. So this is great. And yeah, this is I think, very successful first step with this little playing around with trying to dissolve neodymium magnets. I'm hoping that we can actually sort of dissolve and then separate out the neodymium and maybe make a few grams of neodymium oxide powder or something like that. But that'll be in the future. We'll see how that goes.